So we are pleased to have Elijah Bodish, and he will tell us about R-matrices.
Okay, yeah, I'm happy to be here. Thanks for letting me participate in the seminar. And so I'm talking about the R-matrices, basically based off of this chapter 7 in the book by Janssen. And in terms of the talk, I doubt that I'll be able to monitor the chat. And so if you have questions, interrupt or chat with somebody who's comfortable with interrupting, and I can try to answer them, or one of the many experts who are present will be able to answer them. So I'll just start with sort of the motivation that Janssen gives for this R-matrix construction. And that's like my chapter 0 here.
And you may want to use a finer pen.
Thank you.
I mean, you can regulate the thickness of the line. There is a button that you can press and make the thickness independent of the pressure.
I think I actually have never done that. And instead of doing it in front of everybody right now, I'll just use the thin line, but that sounds nice. So the setup is, and I'll recall more precisely what U is, but for now, we just have to recall that U is a Hopf algebra. And so if we take two representations, V and W, for the algebra U, and I'll try to be consistent about this. If I write little m mods, this is going to be for finite dimensional vector spaces with the U action, and then I'll also try to keep track of this type 1 representation just by using a superscript for my notation. And so we have, since use a Hopf algebra, there's an action on tensor products of these vector spaces, V tensor W and W tensor V. And the way that this works is there's a co-multiplication. So if we have U and U and write delta of U is, say, the sum of UI tensor UI prime, then the action on a vector in V tensor W, little v tensor little w, is going to be this sum of UI acting on V tensor UI prime acting on W. And I'll just define now a different co-multiplication, delta op, which maybe I'll define right before that. P, which is going to be some universal notation for a map between the tensor product of two vector spaces that flips simple tensors. So for any two vector spaces, I'll define this map P, which sends a simple tensor A tensor B to B tensor A. So delta op is this map delta composed with P. So this is from U to U tensor U by delta, and then I flip factors. And now there's an action on W tensor V by U via delta, which would be the usual, for our choice of co-multiplication, usual action on this tensor product. And then I also have an action on V tensor W via now U, if U were to act by delta op. And just from the formulas that I've given, we can see that if I wrote P of U acting via the usual delta on W tensor V, this is going to be the sum of UI prime acting on V tensor, UI acting on W. And so that's actually, this is U acting on V tensor W, but through this delta op. And so the map between these two vector spaces P that flips the simple tensors is not actually going to be a U module intertwiner in the case that delta is not equal to delta op. So there's kind of this, there's sort of two issues here, is that for RU, which is UQ of G, there's two things happening. One is that delta is definitely not equal to delta op. Remember, delta was defined just on generators, and from those formulas, you can see that it's not equal to delta op. But at the same time, we do know that abstractly V tensor W and W tensor V are isomorphic as U modules. And that's because, I guess, in the first or second talk that Leonardo gave, there was this discussion that the tensor, decomposing a tensor product of U modules, like it's sort of just determined by its formal character, and then you can think about just how it decomposes as a G module. And so V tensor W and W tensor V are isomorphic. I mean, their analogs are isomorphic. Their analogs as G modules are isomorphic when you tensor product them together, because the usual enveloping algebra does satisfy delta equals delta op. So we have these two things, and we kind of need to remedy them. We want to find...
and perhaps a remark is that here you use that Q is not a root of unity.
Yes.
Already. Otherwise, the argument doesn't work.
So we can just kind of compare to G modules. So what we're attempting to do now is, instead of using this flip map as our isomorphism, we're going to work harder to come up with some sort of a nice isomorphism between V tensor W and W tensor V that commutes with the U action. So maybe I'll just try to continuously scroll this way. Let's suppose there are isomorphisms.
Oh, sorry.
Yes.
If Q is roots of unity, does isomorphism fails?
Well, I mean, it depends on what you mean by quantum group. For the usual form, it will fail.
Okay.
And we'll later discuss Lustig form with divided powers, where this is still the case. Well, the isomorphism still holds, and we are essentially the same in the same way.
Okay. Okay. Thanks.
Well, for usual form, it fails almost. It still doesn't fail almost everywhere. So you will have big center, and representations will have central character, and our matrix is defined. It's a rational function, so it will have poles, but for most values, it still makes sense.
I see. Thanks.
Excellent. So yes, we're just going to suppose that there's some isomorphisms VW from, or R sub VW from V tensor W to W tensor V, which are actually functorial in V and W. And there's just kind of this awkward thing to do in the motivation part, is that even though eventually we're not going to get this for all V and W, it's just going to be for V and W, which are finite dimensional type 1 representations, we'll say for all V and W. We're just a caveat that this is for motivation only. And the functoriality means that explicitly I'll have this map RVW from V tensor W to W tensor V. And if I take a map, say F from V to V prime and G from W to W prime, then this diagram will commute. So this sort of motivational assumption that we have such an isomorphism for all pairs of representations of U, we can plug into this the left regular representation. So if we consider R U U, where U is the left regular representation, this gives us an isomorphism from U tensor U to U tensor U. And this sends the identity, which is 1 tensor 1, to some element, which I'll call R. Now, in order to sort of make use of this element R, we just observe that for a module M, for the algebra U, and an element in that module, we get a U module homomorphism which I'll call rho sub M, right multiplication by M basically, which is going to be from the left regular module to M, and it sends an element U to U acting on M. And now for V and W, some pair, we can compute R VW applied to some simple tensor in this tensor product of V and W. And we can compute this as follows. We could say that this is equal to R V comma W composed with, I have this right multiplication by an element homomorphism, so I can use two of them to get rho V tensor rho little w and apply that to 1. So this is just a way of getting V tensor W by acting on 1 by this tensor product of two right multiplication maps. And now, because of this assumption of naturality, I can rewrite this as rho W tensor rho V composed with R of U of 1. And that is equal to rho W tensor rho V of, well, R of U of 1 is this element R, which I'm trying to get into the picture through this little calculation here. And then to compute the image of rho W tensor rho V on R, well, R is this element of U tensor U. So I actually just act by R. So this is going to be R acting on W tensor V. And so the only thing left to observe is that I started with V tensor W, and I end up with W tensor V under this, doing this calculation. So I actually need to, if I kind of want to write R sub VW in terms of my element R, I need to also introduce the element P on the right, where P swaps these simple tensors. So this is RP of V tensor W. So this is like just the little motivational calculation that tells us that if we want this family of natural or of functorial isomorphisms between V tensor W and W tensor V for all V and W, we're going to be led to finding some element R, which, if I precompose with the flipped map, actually realizes this family of isomorphisms. And then there's a few properties that you can observe about this element R based off of what you sort of expect this R sub VW to satisfy. So this is just still kind of commentary on motivations, that since R blank blank is a natural isomorphism, expect R is invertible. Okay, and then also since R blank blank is a U module homomorphism, we expect that R, maybe I'll put this a little bit more displayed, R delta op of U is equal to delta of U R for all U in U. So the sort of the short explanation of why we would expect this equation. So this is just, I have my element R, not my family of natural isomorphisms. So I sort of am excluding the P from this notation. So if you want to compute this just to check it, you would say, well, R delta op of U, this is this calculation in U tensor U, this is equal to R UU of delta of U. That's because delta op is P of delta. So I can get the P in there to rewrite my R as RUU. And this is RUU of, well, U acting on 1. Remember, delta gives me the action of U on U tensor U. And so this is equal to, since I assume that RUU is a U module homomorphism, U acting on RUU of 1, and then again, this is my delta of U of R. So I want a family of natural isomorphisms between V tensor W and W tensor V. I end up finding that that can kind of be constructed out of this element R, and my element R, I need to satisfy this R delta op equals delta R condition. So what is this element R? Like we don't know anything about it at this point. We just sort of know that we might want something like this element R if we want a system of natural isomorphisms. So that's basically where we're going. The backstory is that Drinfeld defined an element R in a completion of U tensor U. So it's not an actual element of U tensor U, it's in some completion. And this is going to sort of have the general form that R is equal to something that I'll explain in a second, composed with something else that I'll explain in a second. So on the right-hand side in this dot, 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 we're going to have a sum of elements in U minus tensor U plus. And I think that there was a comment last time or 2 times ago about this R matrix being in some sense the inverse, or at least being built out of this pairing, non-degenerate pairing between U minus and U plus that we studied in the last 2 talks. And so using in order to get this sum of elements in U minus and U plus, we're going to be exploiting that pairing. And then how to make sense of this. So these Q to some powers, these aren't elements of U tensor U. So this completion is something that we don't quite know how to make sense of, but what you should be thinking is that this is like a bunch of elements where, I guess, H alpha and H alpha prime are dual bases of H in G. You would have something like Q to the H alpha is K alpha. But, right, this is with respect to the W invariant symmetric form on H. But the issue is that we don't have these elements, and we also don't have arbitrary Ks for like K. We don't have K sub a weight, for example. We only have K sub a root. And so kind of overcoming these issues is a little bit of the difficulty that Janssen goes into more detail to do. But this is sort of our motivation, that our actual consistent family of isomorphisms is made out of this element R, precomposed with the flip map. And the element R is 1 plus some sum of dual basis elements in U minus tensor U plus with respect to this pairing. And then there's some extra factor that's like scaling by multiples of Q, that's giving us different powers of Q. And we'll sort of deal with those two things separately. So this is the end of the motivational part, or the introductory part. Janssen's book just uses this as motivation.
And there is a clear reason why we cannot succeed with our original goal of finding R inside of U tensor U, is that there are relatively few invertible elements in this tensor product.
See. Okay. So I'm going to move on to trying to be more concrete. Are there any questions before that?
So here we have the form Q to the V tensor. Oh, okay. Q to A tensor B. Like, how does this really act on? Like, how does this really affect on a given representation? So I get that QH alpha is K alpha.
Mm-hmm.
And probably we have a dual, but what does Q to the something tensor something really mean?
So, Rinchen, in order to answer this question, you should think how this element will act on the product of two weight vectors. So your weight vectors, weights are still the same thing as weights for the semi-simple V algebra.
Ah. So why don't we write Q to the H alpha and then tensor Q to the H alpha prime?
Because it's not what's going to happen.
Okay, I see. Okay, thanks.
They're not the same.
So if you have weight lambda and mu, what will happen is it's going to be Q to the inner product lambda with mu. And if
not the inner product, not the sum.
I see.
Product of lambda mu, not the sum of lambda mu.
I see. So this is a very shorthand thing. Okay, thanks.
Okay, great, thank you. So, so for the first actual section, I'm just going to go over the R matrix in the example, where it's most easily understood for UQ of SL2. So here K is, as it's been through the beginning of the seminar, is a field characteristic 0. And Q and K is transcendental over the prime subfield. And U will denote UQ of SL2, which has generators E, F, and K subject to some relations. And I won't recall the relations, but I will recall the co-multiplication. We have delta of E is E tensor 1 plus K tensor E. Delta of F is F tensor K inverse plus 1 tensor F. And delta of K is K tensor K. So now if we take V and W in U mod type 1, then we're going to follow, and now we're following Janssen now. So if you've read this section, hopefully most of what I say is familiar. So the state of EW is going to be equal to 1 plus, and I take a sum over all n bigger than or equal to 1, negative 1 to the n, q to the negative n choose 2, q minus q inverse to the n over quantum n factorial, fn tensor en, and that's acting on V tensor W. So this is Drinfeld's R matrix, but acting on V tensor W without the weird Q part. And this makes sense because, well, V and W are finite dimensional modules, and we know that E's and F's act nilpotently in all finite dimensional representations. And so some power of Fn, some term for Fn tensor En will be 0 on V tensor W, and all higher powers, all higher terms will also be 0. So this is just some finite sum when you plug it into a representation. Furthermore, since it's 1 plus, and as I just said, all of these terms, which are built out of my Fn tensor Ens, these are going to be acting nilpotently. I have 1 plus nilpotent element. So this state of VW will be a unipotent element in the representation, and that means it'll be invertible. So let's see just in an example of what this looks like. So we have this definition. I mean, let me point out that like this, I guess, basically this term is fairly familiar from the calculations that we did last time when we were computing with the bilinear pairing on U minus and U plus. And here's our U minus and here's our U plus. More on that later. So for our example, we'll take V, which is the first fundamental representation for U, and we can kind of just draw the quiver or whatever you want to call it for this representation, where I have pictures of how my E's and F's and K's act. So I have two vectors, V and FV, and F takes V to FV, and E takes FV to V, and then my K's, well, K acts on V by Q, and K acts on FV by Q inverse. So this is this two-dimensional vector space. I can tensor it with itself, and I get a four-dimensional vector space. And it has a basis, which I'll just order so I can write a matrix, V tensor V, V tensor FV, FV tensor V and FV tensor FV. And it's I mean, I don't even know if to call this an exercise or what, but if you use the definition above, if I did theta VV, there's going to be 1 plus -1 times Q minus Q inverse F tensor E acting on V tensor V. The point is that F squared acts on V as 0, E squared acts on V as 0. And so basically theta VV is just made out of 1 and then a single term, this first term with F and E. And in that case, the n choose 2 term just gives me 0. And so I have Q to the 1, which doesn't appear. And then my quantum n factorial in the denominator is just 1 factorial, which also doesn't appear. So I just have the Q minus Q inverse. I have -1. And if I wanted to be maybe even more concrete and write this in a matrix with respect to my basis, you can see that it looks like this. I have 1s along the diagonal as expected, and then one single off diagonal term here, which is Q inverse minus Q. So this is, more or less how we're expecting this theta to look. And remember, this element theta is not really quite the analog of our element R. We have to insert into it somehow this confusing Q to the sum of H tensor H prime, and that's what we'll do next. So instead of trying to make sense of this element Q to the sum of H tensor H prime in some completion of U tensor U, Janssen's approach is more down to earth. It simply introduces some linear maps which will act on weight vectors as we want it to. So Janssen's approach to Q to this term is as follows. And the one thing maybe keep in mind, although, sorry if this is confusing, but for SL2, alpha alpha is 2. And so we might want Q to the H alpha tensor H alpha over 2. So let lambda denote the weight lattice, which is lambda is Z times this fundamental weight. And we have to, basically because of this 2 in the denominator, we have to make some assumption. We have to assume that Q has a square root in this field K. So I didn't need this assumption to write down my element theta, but I am going to use it at this point. And I define F from lambda cross lambda to my ring K by F of A, B. So I'm just going to identify it with the integer so I don't have to write my fundamental weight a million times. This is equal to Q to the negative AB over 2. So that's just a function. I want to get a linear map. So for V and W in U mod type 1, I'm going to define F tilde from V tensor W to V tensor W by, well, if F tilde, if I restrict it to something like V lambda, the lambda weight space in V tensor W mu, the mu weight space in W, this is going to be F of lambda mu. Lambda mu's, those are just 2 elements of my weight lattice, times the identity. So I'm just going to rescale these vectors by F of lambda mu. And maybe more concretely, this is if I if I had V tensor W inside of these things, this would map under F tilde to F of lambda mu times V tensor W. So this is our replacement for this Q to the sum of H's. And we needed a square root of Q just to even define this, since we're dividing by 2, or we're dividing an integer by 2 in the formula here. And this is.
I have a quick question.
Yes.
Could you please scroll up a little bit?
Mm-hmm.
So you have Q to H tensor H prime. So why do you have minus sign?
That I mean, that I don't know. This is just This is sort of just motivation. I don't have a good reason for that. I don't have a good reason for that.
Yeah, most likely there should be Q to minus H tensor H. It depends on what coproduct you use. So.
Okay.
Yes. No, that's I don't have like a good reason for that, but yes, I mean, I probably ignore this thing from now on.
I mean, most likely is the Greenfield uses different kind of coproduct than Janssen, and so to go from one to the other, you need to change the sign, something like that.
Okay. So okay, so the thing that I'm just going to write down here, maybe it should be ignored, but I just want to make this point now that if I define f of AB as Q to the minus AB over 2, then I'm going to have f satisfying various conditions. So like I'm going to have f of lambda mu plus nu equals f of lambda mu, f of lambda nu, f of lambda plus mu nu is f of lambda nu, f of mu nu. I'll have f of lambda mu plus nu is also Q to the negative mu lambda, f of lambda mu, and f of lambda plus nu mu is Q to the negative nu mu, f of lambda mu. And it's just an easy check to see that this formula satisfies these two things. And somewhere along the lines, we'll use them, and I'll probably recall them as needed. But I wanted to point out that these are required for two separate things. So this is needed for what will be the hexagon equations to hold, and this is needed for theta delta op equals delta theta. So one of the things, if you read the chapter 7, it's kind of, Janssen sort of breaks this up into two separate cases and works just with an arbitrary function f that satisfies this condition throughout and ignores the extra requirement that you need to put on f in order to satisfy the hexagon equation. So I guess basically what he ends up arguing is that just if you satisfy this formula, you don't have to have square root of q, for example, in your field, and you'll still have some nice properties. But just for the ease of exposition, so this is really only for people who are kind of like way ahead of us, that I'm going to be just assuming everything at once. We're going to get hexagon and the theta delta op equals delta theta altogether. But of course, if you look in the book, you can kind of get rid of this square root of q at the cost of getting rid of this. But that's maybe a little bit more of an advanced topic. So then now that we have,
Are you talking about SL2 right now?
just talking about SL2 right now.
Okay.
Yeah. So I mean, these could just, I mean, lambda mu and u are A, B, and C. So we would define RVW to be theta WV as defined, composed with this F tilde, which is like our Q to the sum of the H's or minus H's, and then composed with this P. And so again, this is our version or Janssen's version of Drinfeld's R. And as we discussed, once we get our element R, we can get R sub VW by precomposing with the flip map.
Why
So
do
the
we need P?
What's that?
Why do we need to compose with P?
So this was like this calculation they did way back when, 20 minutes ago, where
he's objecting that P shouldn't be part of R in your
That's right.
formula.
There's not. So this part is, this is what I'm saying is our version, your Janssen's versions of Drinfeld's R. But R sub VW, this consistent family of isomorphisms from V tensor W to W tensor V, this does require V.
Okay.
Yeah, so maybe I should have gotten, so maybe I should have used like sigma or something for my R sub, sigma sub VW instead of R sub VW, but I just decided to go with R sub VW. So the theorem is that RVW from V tensor W to W tensor V, and this is really theorem 1, just for the SL2 version, is an isomorphism of U modules and is, maybe it's just not even parenthetical, this is pretty important actually, functorial in V and W. So the proof of this is postponed. Since we're really just still at the SL2 case, I want to instead look at an example. So back to V equals the first fundamental. So we had this explicit description of this module and how E, F, and K act above. I knew that my element theta was something like the identity with a little extra term here, which was a minus Q minus, or negative Q minus Q inverse. And I'm then going to make my element R V tensor, or V comma V, out of this, some F tilde, and some flip map. So because of the basis I chose, it fixes V tensor V and FV tensor FV, and it swaps these other terms. And then I have my Q tilde. Well, A and B are both 1 in this, or I guess, yeah, they're both 1 in this case. So I just have, or they're 1 and minus 1. So I have Q to the negative 1/2, Q to the 1/2, Q to the 1/2, and Q to the minus 1/2 on the diagonal. So my R is built out of these 3 terms. So my matrix, if I write it explicitly in terms of this basis for V tensor V, is built out of these 3 terms. And so I end up having something that looks like this. So I can't get rid of these Q to the 1/2s. I've got Q to the negative 1/2. And then I have kind of a middle 2x2 block matrix. There's a 0 here. I've got Q to the 1/2, Q to the 1/2, Q to the negative 1/2. And in this bottom right-hand corner, I have Q to the negative 1/2 minus Q to to the 3 halves. So there's some kind of slightly messier version of the element theta that we had above, permuted by the element p, and then scaled somewhat by these powers of q to the 1/2. Okay. So the second main result that we want is some sort of a consistency for these R sub VWs. So this is what's going to be called the hexagon equations. So before I can write down this theorem, I just have to recall that we have these canonical isomorphisms which reassociate simple tensors and do it the other way too. And these maps can, if I'm looking at A tensor, B tensor, C, if the 3 of these are U modules and I'm trying to define a U action on them, there's 2 obvious ways. I could act on A tensor B and then act on A tensor B tensor C, or I could act on A and B tensor C and then act on A tensor B tensor C. And because our element U, the co-multiplication is co-associative, these maps are actually U module isomorphisms. So if A, B, C are in U mod, can is a U module map. And these canonical isomorphisms just play a role in the thing that I'm about to write down. So the second theorem, which is going to be true in general, but I'm just sort of in theory stating it now only for SL2, but it's true in general, is that the following diagrams commute. So the first one is about starting with V tensor W tensor X and traversing some hexagon. So I could start by applying my element R to the W and X terms, and I would get V tensor X tensor W. I can use this canonical isomorphism to reassociate this and get V tensor X tensor W. And then I can use my R isomorphism on V and X. So I could do R V X tensor the identity of W, and this gives me X tensor V tensor W. So if I just reassociate first, so I use my canonical isomorphism here to go to V tensor W tensor X, now I can actually do something which is going to be a little bit more complicated, but this is R sub. I can think of V tensor W just as a U module, and I can use my R for V tensor W comma X. And this will send me to X tensor V tensor W, which then there's a canonical isomorphism with the right-hand side. And 2 is sort of the same, but start with V tensor W tensor X on the left-hand side. So I'll just leave that as something to do while you're listening to me blather on. You can write out that diagram. So again, proof of this will be postponed. We'll prove it in the general case at some point. The thing that I just wanted to note is that this R V tensor W comma X, like I said, I mean, it makes sense, but it's a little bit more confusing maybe how to write it. So this is going to be, again, I use my element theta, but now for X and V tensor W, I'm going to have some F tilde and I'm going to have some P. And so I need to make sense of this theta. And so the point is that this is equal to the identity tensor my co-multiplication evaluated at my old theta. And then applied, I mean, the theta, which is just this formal sum, and then applied to my representation, X tensor V tensor W. So these are the two main results. We sort of are going to, in general, define the element R by using the pairing between U minus and U plus. And then the two results will be that first, we can prove that this is actually an isomorphism of U modules. So we need to prove that it commutes with the action of U, and then check functoriality in V and W. And we'll also prove that, so I'm calling this theorem 2, these hexagon diagrams commute for all V, W, and X, which are type 1 representations. And the nice thing that comes out of this, maybe this is hopefully the last thing I can say and then we'll take a break, is that, so, I mean, why do we want the hexagon? So this is a bit of a story, but basically, if you think about this notion of a braid, so a braid in n strands is, so there's a formal definition which you can read in the second reference I gave, but for us it's just going to be some picture that's like a picture of a braid. So this is a braid on 5 strands, and the picture is taken up to isotopy, I guess, relative to the boundary. And there's a product on pictures up to isotopy of this. So if I have one picture beta and another picture beta prime, I can multiply them together by stacking the diagrams. And this product makes the set of all braids on n, this is fixed, strands. Again, taken up to isotopy, a group. So this is made up, makes these isotopy classes of pictures relative to the boundary, where the boundary are n points on one side and n points on the other side. Multiplication is stacking. The identity element is just going to be the trivial braid, which has no twists or crossings in it. And this is made into a group. And then the theorem, which you can't help but citing, which is a theorem of Artin, is that if I denote this group BR sub n has a generators and relations presentation generated by sigma I for I is 1 up to n minus 1, subject to what are called the braid relations. So I have sigma I plus 1, sigma I is sigma I plus 1, sigma I plus 1. And I have sigma j is sigma j, sigma I, when I minus j are sort of, I guess, we would call it far apart, where the absolute value of the difference of those two indices is greater than 1. And how does just the map work is just that the element sigma I will map to the braid that, I remember I've got n strands on the, or n points on the bottom, n points on the top, n strands total. So if I take the ith strand and the I plus first strand and cross them this way, doing just the identity strand on all the other strands, this is where my element sigma I goes. So important thing for us is these two relations. So the first braid relation is we'll see follow from the hexagon identity. So hexagon equation will imply braid relation.
Maybe you want to say that all your three spaces are the same.
On the R's, yes. On R, when V equals W equals X. So let's see. Maybe I will.
Maybe you want to write down which R's you mean.
Yeah. So let me see if I can say it this way. So let me see if I can get away with saying it this way. So even more generally than the case where V equals W equals X, I can take a morphism R VW, and I can associate to that a braid just on two strands like this. But I guess I'll have to sort of label it by, or in fact, I choose not to label it. And if I have some composition of products of these R matrices, so some complicated, I mean, maybe I'll just do it as an example. So if I look at the top of my hexagon identity, I had the identity tensor R one. So if we look at the top of my hexagon identity, I have the identity tensor RWX. I have the.
Would it be possible to just write a braid relation for on V tensor V?
Yeah.
That's known as Young-Baxter equation.
I can do that, sure.
You know, like one product is equal to the other product.
So the Yang-Baxter equation is motivated by this braid relation. So on the braid side, if we write our braid relation, by it in pictures, we mean this. And so the left-hand side product in terms of R matrices is going to be, I first take RVV, tensor the identity, I compose that with the identity tensor RVV, and I compose that with RVV, tensor the identity. And this is equal to, well, my right-hand side, this is identity tensor RVV composed with RVV tensor identity composed with identity tensor RVV. So this equality between maps between tensor products of, this is, I guess, equality in and U of V tensor V tensor V. So the point is that we'll be able to derive this Yang-Baxter equation from the hexagon equation. So hexagon and functorality for R imply Yang-Baxter. For RVV. So that's the equality of this left-hand side and right-hand side of elements built out of identities and RVVs for any V, which is a type 1 finite dimensional representation of U. And then the proof of this is that you can take the left-hand side and by the hexagon identity, the left-hand side is, it's like, I mean, this is sort of the top row of my hexagon identity. So or I'm sorry, this is the top row of my hexagon identity. So I can rewrite this as RVV tensor identity, and then I compose with R V comma V tensor V. And then functorality, I can think of RVV and identity as like my F and G in my functorality diagram at the very beginning. And this allows me to commute that RVV tensor identity past this RV comma V tensor V. And so this is equal to R V comma V tensor V composed with now the identity tensor RVV. And then I use the hexagon one more time to get the right-hand side. So
somehow doesn't look right.
Okay.
RVV is not a tensor product of two maps, right?
So the point is that this is I'm using naturality where this is my R, this is my F, and this is my G. Does that hold water?
No.
So my naturality said that if I had F tensor G composed with R of, I don't want to write A, or I don't want to write V. So let me do F from A to A prime, G from B to B prime. Probably I'm wrong, but let me just write this. This is RAB. This should be equal to RA prime, B prime, G tensor F.
So Vanya, can you explain what is the problem? I mean, this R switches components. It's not the R matrix.
Okay. So then there is no problem. Sorry.
Yeah, maybe right. This stupid thing. I should have just written sigma instead of R, probably, or some other notation. But yeah, this is the isomorphism. This isn't the actual R matrix. Is that basically the confusion?
Yes, thank you.
Okay, I guess probably this is a good place to stop, and then when we come back, I'll talk about the arbitrary, or I'll talk more about arbitrary G.
Yes. So let's see if people have questions.
Right.
Well, I had a kind of meta question, which is like, why are we interested in this R matrix?
Right. So I guess there's two things. The main thing is that what we just did is that we said that if I fix my representation V, this element R, or this R matrix, or my R sub V, this gives me a endomorphism of a finite dimensional vector space, which is V tensor V, which satisfies this braid relation. And so my understanding is that it was before the introduction of quantum groups, it was very, very difficult to write down linear representations of braid groups. And this gives us a linear representation of braid groups. In fact, it gives us many, many, many linear representations of braid groups. And this Yang-Baxter equation, really the version that doesn't have the P in it, the version just for the actual R matrix, which I have chosen to not write here, that is maybe the original motivation, is what it says in the book for the introduction of quantum groups. But there's people here who know this story much, much better than me, so I'll shut up.
Yeah. So that's the motivation came from physics, because this equation arose in several different areas of physics, including statistical mechanics, quantum field theory, and so on. But in this context, it's important that representation category of quantum group is a braided tensor category, so we can switch objects when you have a tensor product, and so that's what it is for. But actually, it's even more important than that. Actually, more or less anything about quantum group can be, read off from the R matrix. There is actually a construction of quantum groups, which is called the Fadeev-Reshetykhin-Takhtajan construction, where you construct them out of the R matrix so if you have just these solutions, you can build quantum group just from that.
And we'll sort of see it when we discuss quantum coordinate algebra.
Yeah, and so basically our matrix contains all the information about quantum groups in it. Well, at the elementary level, not about canonical basis so much, but the algebraic theory of quantum groups basically contains all the information.
Maybe if I can complete, Pavel, one more thing about what you said about the R matrix and the reconstruction of the quantum group. It's the R matrix for the two-dimensional, we take V and W, the two-dimensional, V equal W, the two-dimensional representation of SL2. And this R matrix, kind of the smallest non-trivial one, the RVV, is enough to reconstruct the quantum group. It's not the abstract R matrix, somehow, which itself doesn't make sense if we haven't yet the quantum group. If we think of the one living in the enveloping algebra, tensor enveloping, in U tensor U.
Okay, let's we reconvene at 5:15, and meanwhile there is a question from Roma in the chat.
Yeah, yes, our matrix is unique up to so you can ask the question categorically, which is that there is representation category of quantum group, and how many braidings does it have? So it has two braidings. Any braided category which is not symmetric has always two braidings, because you can take ordinary braiding and inverse braiding, and that's the only ones that quantum group has. Well, if you only restrict yourself to type 1 modules and so on, and sometimes you can twist by side, so it's not completely true. There is some trivial kind of twists that you can do, but basically, if you work over rational functions of Q, there isn't much choice.
Sorry, so here you were kind of assuming that you already have the deformation of the tensor category, right? You have already the tensor category, and then you're saying how unique is. Yeah, maybe you just clarify what was given in your answer and what is then unique.
Yeah, the tensor category has just two braidings basically. well, at least if you restrict to adjoint group, that's for sure true. If it's not there might be some twists that you can make, but
so you say braiding, so you already have the associativity constraint, but you do not fix.
That's correct, yes.
But you do not yet fix commutativity, and then you're asking.
That's right. So in fact, you can ask the question about deformation. So you can ask the following question. You have a category of representations of your group G, which is a symmetric tensor category, and you can ask for its deformations in two different ways. You can ask deformations of tensor category, and you can ask deformations of braided tensor category. And in both cases, modular space of deformations is one-dimensional. The deformation is unobstructed, and there is only one first-order deformation. But these spaces are not the same. One is a double cover of the other. The parameter for deformations of categories is square of the parameter for deformation of braided categories. And so this is a 2-to-1 map, and that's why each category has two braidings.
Thanks.
Okay, any more questions, comments?
Well, no, so only two braidings up to, Ben is saying only two braidings up to scalar. So scalars are, you cannot rescale braiding just obviously, because braiding satisfies a nonlinear equation, which is hexagon. So sometimes you can rescale it by some scalars depending on representations if you have a grading on the category by some abelian group. And this is true if your group is not adjoint. That's why I said that for non-adjoint groups, you may have some issues. There are some simple twists you can do. But otherwise it is unique. And also there is a question, so from Georgie, there is a comment that for SL2, we can get everything from the two-dimensional representation because of the Schur-Weyl duality. So you have this Heike algebra, and that's also true for SLM, right? So you can, and that's how Fadeev-Reshetykhin and Khartajan construction actually works, through Schur-Weyl duality, more or less. Can we see uniqueness from some cohomology group? Yes, you can see uniqueness from some cohomology group. That's right. Right. Recovery of quantum group from R-matrix is some general thing about Hopf algebras and braided monoidal categories. Yeah, yes, it is a general thing about Hopf algebras and braided monoidal categories. If you have a braided category, well, it's a thing about braided categories together with a fiber functor to vector spaces. So if you have a braided category with tensor functor to vector spaces, which in our case is forgetful functor, you can construct the Hopf algebra, and it is indeed called coend, as Elijah points out.
Okay, perhaps we can resume.
Okay. So, I had at some point made some notes about talking about the general notion of braided category, but this is probably maybe best left for the discussion. So I just want to make a point again that we're putting this extra hypothesis on this function f, and that extra hypothesis makes it so that our matrix or our consistent choice of isomorphism, our VW, satisfies the hexagon identity. And the point of the hexagon identity is that it allows you to basically give a map of between tensor products of representations for the quantum group built out of canonical isomorphisms as well as the R matrix without determined just by an element of the braid group up to equality. And this is something that basically everybody was just talking about, and so I don't think I'll go into it, but the reason that we're putting this extra hypothesis on our function f is that we want the hexagon identities. In general, it seems that you still have a solution to this Yang-Baxter equation, but it's nicer, at least for us, to just deduce Yang-Baxter from the hexagon identity. So our real goal is to define the R matrix in general and then prove theorem 1 and theorem 2 in general. Theorem 1 was R matrix actually is a U-module isomorphism. Theorem 2 was hexagon identity. So section 2 is R matrix for UQG. So same field, K characteristic 0, Q and K transcendental. And at some point, unfortunately, we're going to have to further assume that that Q has like an nth root for some n in K. So if I have this semi-simple E algebra G, remember this gives rise to a root system, and it has this form, which is the unique W invariant bilinear form on Z phi with alpha alpha equals 2 for short alpha. And then we're going to choose simple roots. Pi, which is alpha 1 up to alpha L for our root system. And this is the input we need to define U, which is UQ of G, which is the K algebra generated by E alpha, F alpha, and K alpha for alpha simple, subject to relations. Again, so I'll just say, if you're needing to be reminded of them as we're reading, hopefully you have the book with you and you can look at Janssen's section 4.3 where he writes down these relations. Again, U is a Hopf algebra with co-multiplication given by these formulas. So just as I'm writing these down, just kind of remind yourself that what we're doing is trying to relate delta and delta op. And so you can see from these formulas that delta and delta op will be different. And there's, of course, co-unit and antipode, and you can see that in section 4.8 of Janssen. Then there's some subalgebras of U that we had to focus on in the last talk, or the last two talks, I should say. And that was U plus, which is the subalgebra generated by the E alphas for alpha simple, and U minus, which was the subalgebra generated by the F alphas for alpha simple. And we proved in the first talk that this is isomorphic to the algebra generated, the free algebra generated by the E alphas subject to the quantum Serre relations. Same here. so this is the subalgebra, and it's presented by generators and relations. That was kind of the content of the first talk. And then u greater than or equal to 0. This is the subalgebra generated by, well, we've got E alphas and the Ks. And u less than or equal to 0. This is the subalgebra generated by F alphas and Ks. You know, again, all of these.
You have K to plus minus 1, not F to plus minus 1.
Yeah, thank you. So the main thing also is that all of these subalgebras, as well as the algebra itself, are graded by the root lattice. And we'll write, like, if A is one of my algebras or subalgebras, A sub mu for mu and Z phi to denote the vectors which transform by weight mu. Or in the mu graded space, weight space. And then last time we went into the following, which was a proposition in Janssen's book, which is that there is a bilinear pairing from, I guess, between u less than equal to 0 and u greater than or equal to 0. And it's given, again, kind of basically by generators and relations. So this is uniquely determined by we have this bialgebra pairing, I guess is what people were saying last time, property, as well as the one in the other direction. So if you remember kind of last time, I believe we were using this convention as a convention in the book. Y's, elements that are like Y's, you should think of those as being in U minus or U less than or equal to 0, and X's, those are things in U greater than or equal to 0. And then we can pair the K's like this, and then the F alpha E betas pair, well, if they're distinct simple roots, it's 0. And if they're the same, I get -1 over Q alpha minus Q alpha inverse. And then the K's and the E's and the K's and the F pair to 0. So yeah, so this is Janssen proposition 612. Oh, and I should maybe remind you, what do I mean in like these formulas? So if I have A tensor B, C tensor D, I'm extending my pairing on U cross U, or U less than or equals 0 cross U greater than or equals 0, to U tensor U cross U tensor U by just multiplying. So I pair A and C, and I pair B and D. Okay, and then the proposition from Janssen that's maybe more what we need is that for mu in the root lattice, which is a positive linear combination of positive roots, the restriction of this pairing to U, so I look at the minus mu graded part of less than or equal to 0, and the positive mu graded part of U greater than or equal to 0 is non-degenerate.
And perhaps we can say the same for when we replace less or equal and big or equal by strict signs, right?
Sure. So yeah. or once I get rid of the equals, I have to flip the sign for some reason. Okay. So this is kind of a reminder of what came before. And in some sense, I mean, everything that we do with this proving theorem 1 and theorem 2 for the R matrix is based off of calculations that were done in the last 2 talks with respect to this pairing. So this bilinear pairing, it gives us basically all that we need in order to make sense of this R matrix. So I'm about to define the actual theta element when G is general, not just for SL2. So first, we choose a basis. And this is going to be fixed throughout. So I'm just going to fix a basis, V1 superscript mu through V R of mu superscript mu. And this is a basis for U minus mu minus. And using that my pairing is non-degenerate, we can choose dual bases. And I'll just write it this way, and a basis U1 mu up to U R of mu mu for U sub mu plus, which is such that V I mu paired with U J mu is delta ij. So these are dual bases with respect to this non-degenerate pairing on U less than 0 minus mu and U greater than 0 minus or plus mu. And then we set theta mu. So this is just one component, one sort of summand of our element that we're going to eventually define theta. And this is just equal to the sum over dual bases elements. So I equals 1 to R of mu, Vi mu tensor Ui mu. This is an element of U tensor U. So some comments on these elements theta mu's. Well, if I look at U plus or U greater than 0 in the 0 wave space, this is just spanned by the identity. And that's also equal to U minus in the 0. And since 1, 1 is 1, this tells me that theta 0 is 1, or 1 tensor 1 in U tensor U. The other comment is, well, if I look at U n alpha plus, this is spanned by a single vector, E alpha to the nth power. And if I look at U minus n alpha minus, this is spanned by a single vector, F alpha to the nth power. And we computed last time that if I pair F alpha to the n with E alpha to the n, I get -1 to the n, Q alpha to the n choose 2, I guess should be negative. No, sorry, Q alpha to the n choose 2. And then I have n alpha factorial divided by Q alpha minus Q alpha inverse to the n. You see, if you want to see this, this is in the book, 6.134. And so that means that theta n alpha is, well, I'm not going to rewrite it again, but this is F alpha n E alpha n inverse F alpha n tensor E alpha n. And for G equals SL2, the positive part of U is just spanned by E alpha to the n. It's just a polynomial algebra on E alpha. And the minus part is a polynomial algebra on F alpha. So we actually recover all of the theta mu's for SL2 just from this one calculation with our form. And that would give us, if we summed over all of them, the theta for SL2. So let me write that. So if I wrote U of SL2 plus, this is just isomorphic to a polynomial algebra on the E alphas. The quantum relations are for like rank 2 things. So this is rank 1. So there's no relation. And so the last two calculations recovers all theta mu for SL2. And our theta for SL2 was defined to be, well, I just defined it, I just wrote it out. I didn't actually sort of tell you that it was related to the form, but it turns out it was related. It is going to be related to the form. So it's just going to be the sum of all of the theta n alphas. But really it's just theta n because we don't write alpha usually when we're just working with SL2. So that tells us what we should probably do in general. We define for V and W in arbitrary U of G or UQ of G mod type 1, we define theta sub V comma W as the sum over mu in our root lattice bigger than or equal to 0, such that theta mu restricted to, theta mu acting on V tensor W. Okay, so why is this well defined? Well, it's basically the same reason, but let me just point out the way to see it is that if you take theta mu, this is in U minus minus mu, U plus plus mu. So if I look at it as a map from V in the lambda 1 weight space tensor W's lambda 2 weight space, I end up in the V lambda 1 minus mu weight space and the W lambda 2 plus mu weight space. And since the weights of V and the weights of W, both of these just being finite dimensional modules, these are finite sets. Only finitely many differences of weights can occur because the weight V is a finite set. So it follows that theta mu of V tensor W is 0 for all but finitely many mu. So that means that actually this theta VW thing that I defined is well defined, because if I take theta mu and act on V tensor W, all but finitely many terms in this sum will be 0. So I'm really just taking a finite sum in some representation. And just as in the case of SL2, we can actually convention seems to be writing this stuff in a different color. So also we can choose bases of V and W so that theta VW is 1 plus some upper triangular or lower triangular nilpotent matrix. So again, theta VW for arbitrary G is going to be 1 plus some upper triangular or maybe lower triangular if you order your basis the other way, nilpotent matrix. And so it's an invertible endomorphism of V tensor W. Okay, so that's the definition of this thing theta mu, or theta VW, which is built out of theta mu's, where mu runs over all positive combinations of positive roots. And this gives us our element, which is like the one third of our consistent isomorphism. So let me do an example. So for G equals SL3, I'm just going to write for my simple roots instead of alpha 1, alpha 2, alpha beta. And the Cartan matrix is the same as the matrix for this W invariant pairing because all of my roots have the same length. So this is just giving me my pairing between alpha and beta or my Cartan matrix. And I have a U, which is a UQ of SL3 module. Again, just my first fundamental representation, which I'll write as V. And this looks in a basis like I've got V, I have F alpha V, and I have F beta F alpha V. And I have E's and F's moving me up and down where E alpha acts as 1 here, E beta acts as 1 here, F alpha acts as 1 here, F beta acts as 1 here. And anywhere I haven't drawn an arrow, my E's and F's, my generating E's and F's act by 0. And then my K's act, I'll just write a tuple here to indicate the weight. So K alpha acts on V as Q, and K beta acts on V as 1. And then I act here, K alpha acts as Q inverse and Q, and here K alpha acts as 1, and K beta acts as Q inverse. So this is the Q version of the vector representation for SL3. And I just want to write down what theta VV is in this case. So you can see that any square of E and any square of F will act as 0 on this representation V. So theta VV is actually going to be 1 plus theta alpha plus theta beta plus theta alpha plus beta acting on V tensor V. So the only, I guess, the only theta sub mu's which will act non-zero are going to be one of these four. So that element 1 is giving me my theta 0. The theta alpha and the theta beta, we already know what those are because we computed them just above, kind of in this for arbitrary theta and alpha. So we're interested in this case of sort of what goes into computing theta alpha beta. So to do this, or theta alpha plus beta, I should say. Well, we'll use that. If I look at U plus alpha plus beta, this is spanned as a vector space by 2 vectors, E alpha beta and E beta alpha, or E beta E alpha. And if I do minus, and then this is minus alpha plus beta, this is spanned by F alpha F beta F alpha. And we computed in a previous lecture that if I write C as negative Q minus Q inverse inverse, so this Q minus Q inverse inverse term comes up over and over again, so I'm just writing it as C. Well, in the old lecture, we computed that if I use my pairing between U minus and U plus, F alpha, F beta, and E alpha, E beta ends up being C squared times q to the minus alpha beta. And then, so this is q to the plus alpha beta. Alpha beta, their pairing is -1. So this is q inverse c squared. And then it's from that calculation, if you followed how to do that calculation, which maybe it would be a good idea to go back and look at it if you are forgetting, but you can complete the exercise, which is to check that the pairing matrix between u minus alpha plus beta, or u plus alpha plus beta and u minus minus alpha plus beta is given like this. So it's just c squared times the matrix q inverse 1 and 1 q inverse. And then the dual basis is given by, well, I'd have f alpha, f beta, f alpha, and c inverse. Maybe I'll just leave it as an exercise also, just to, you know, write down this dual basis with respect to this pairing. I won't give you the answer. I'll leave some of the fun to you. So I guess the only thing I want to illustrate with this calculation is that, like, it's already kind of a headache to just compute theta alpha plus beta on V tensor in general. When we compute this action on V tensor V, it simplifies to some extent, but actually getting your hand on these theta sub mu's can be a little bit difficult. So you need to really understand the pairing better than just kind of your bonehead, like if you were me and sitting down to try to think about it, I'm just going to compute what it is based off of the definition. So there's going to be some slightly clever things coming up that are telling us how to compute with the pairing, but you can see that in practice, like, you kind of, once you know the pairing, you can figure out what these thetas should look like. And so that's our element theta. Let me now give the reminder of Janssen's approach to q to the, now maybe I'm saying, I'll just, I think you guys were right that this should be mine. So reminder. I mentioned how he fixed this in the case of SL2. So in general, you have this weight lattice, and you basically, you just set D equal to the index of the weight lattice or of the root lattice in the weight lattice. So you can see why we had a square root for the SL2 case. And assume that Q has a dth root in K. And then you define our new function f, this is for arbitrary g, from lambda cross lambda to k by f of lambda mu is q to the 1 over d to the negative d lambda mu. Okay, so this is how it's defined in the book. I mean, this is just q to the lambda mu, but the point is that since lambda and mu are weights and we're using this pairing on the roots, you might have some fractional exponents, but the worst fraction you could have is d. And so it's fine just to think of it this way. But you actually, in order for this to make sense, you do need this dth root of q. And then again, f tilde, which really is defined for every two representations in terms of f by f tilde restricted to v lambda 1 tensor w lambda 2 is f of lambda 1 lambda 2 times the identity of v lambda 1 tensor w lambda 2. So this function f gives rise to this map f tilde, which is our replacement for this term, for Drinfeld's q to the sum over dual basis elements on the Cartan. And then again, we have, just really easy in this case from the definition to check that for all lambda mu weights, we have, if nu is a weight, some condition like f of lambda mu plus nu is f of lambda mu, f of lambda nu, and f of lambda plus mu nu is f of lambda nu, f of mu nu, as well as if nu is a root, or in the root lattice, then I can write f of lambda mu plus nu is q to the negative nu lambda f of lambda mu. So this, now that exponent is guaranteed to be an integer because nu is in the root lattice. So this is like the less restrictive part of the definition. And the point again is that this is for hexagon, and this is for theta delta op equals delta theta. So we're going, you can just see that if you just assumed that f was some function from lambda cross lambda to k that satisfied this property here, you would have theta delta op equals delta theta if you believe that we're going to eventually prove this. But you might not have the hexagon. And maybe that's important for some reason, but again, we're just skipping it in this case. We're just assuming that we have a d root. So just because I was kind of embarrassed, but I got confused about this when I was writing up my notes. So let me do a quick example of a calculation just so you see where this d root is coming from. So in the case that my phi is like the A2 root system, so this is SL3. My Dinkin diagram is, well, I have two simple roots, alpha and beta. I wrote down the Cartan matrix above. And then if I invert the Cartan matrix, I get fundamental weights, omega 1 and omega 2. And this is 1/3 to alpha plus beta. And this is 1/3 alpha plus 2 beta. And this matrix gives me the pairing on roots. So I can also use it to give me the pairing on fundamental weights, but you can see already that I have this 1/3 in the denominator. So this is just a reminder of if my formula was, if I just have f of lambda mu for lambda mu in my weight lattice, then this is, like I said, you could just take it to be q to the negative lambda mu. And for example, if lambda was a omega 1 plus b omega 2, and mu was c omega 1 plus d omega 2, then f of lambda mu is looking like q to the negative 1/3, and then I have something which definitely is an integer, 2ac plus bc plus ad plus 2bd. So this is sort of what this function f looks like in general. For SLN, you're going to have a denominator of n. And yeah, maybe for the interest of time, I won't give the example calculation, but it would be a good exercise. So I described theta v above for v equals this L of omega 1, g equals SL3, and description of f for SL3 to write the matrix of RVV where again, just as a reminder, RVV is, I've got theta VV. So that's going to be this operator I built with one theta alpha, theta beta, and theta alpha plus beta acting on V tensor V. And then I compose with F tilde. So I'm going to have some cubed roots of Q running around. And then I'm going to compose with P.
Yeah, so may I make a comment?
Please, yes.
So actually, this brings it back to the discussion that we had a little bit earlier about how many braidings do you have? And so there is a braiding and inverse braiding, but if your group is not adjoint, then there is another freedom which has to do with the fact that the group has non-trivial center. So if your group has a center, then the category of representations is graded by characters of this center. And then you can, whenever you have a braided category which is graded by some abelian group, you can always, if you have a quadratic form on this abelian group with values in C star, you can always multiply the braiding by this quadratic form.
So you're saying for SLN we can multiply the braiding
by character. You can multiply by a by character. Yeah, and so we can for SLN. That's why you have this basically this root, because you have this freedom and there is no canonical choice. So the orbit of the braiding under this action is a kind of free orbit, but it's a torsor. It's not. There is no canonical choice. So you have to choose a root of unity to specify something. And something even more interesting goes on if you take orthogonal group of size divisible by 4, because in that case, for spin groups, the center is not cyclic. So you actually get more. So you have several. You have to choose several roots. So it's there is even slightly more freedom, but basically that has to do. If you have a joint group, you will not have to choose anything.
Okay, thank you. So you're saying basically if we just restricted instead of all finite dimensional type 1 representations, those with that are direct sums of simple modules with highest weight in the root lattice.
Yeah, then you don't have to, because in that case, lambda mu will be an integer.
This is divisible by 3, and so.
Right.
Okay, so there's 5 minutes left technically. I'm basically in my notes, I'm about to I'll just state this theorem and then maybe we can decide what goes next. So this is theorem 1 for the G case. And that is if I let V and W be in U mod type 1, then RVW, which is theta WV, I defined this above, this is this sum over theta mu's, composed with F tilde, this is Janssen's sort of fix to the Q to the sum over dual basis in the Cartan, precomposed with P, this is a map from V tensor W to W tensor V, and this is a U-module isomorphism functorial in V and W. So I could outline the steps of the proof and then we start again. Is that the best thing?
Yes, you could.
Okay. So the proof will be in 3 steps. So the first is we introduce a third co-multiplication, which is going to be superscript tau delta, which is just tau tensor tau composed with delta, composed with tau. I'll write this out more explicitly next time, but the point is that tau is this anti-algebra automorphism, or algebra isomorphism between U and U opposite, defined on generators just by E maps to E, F maps to F, and K maps to K inverse. So we're just messing with how the algebra acts on weights, basically. And we're just changing how Q acts using this new multiplication. And this is something general for anti-automorphisms of a Hopf algebras. If you can twist the co-multiplication, you can also change the co-unit and antipode. And we're just focusing on the action on the co-unit. But the thing that we're going to do is argue that delta of U circ theta is equal to, well, if I commute theta past this delta, this is going to be tau delta of U.
And this is a crucial step of the proof.
This is like the actually tricky part. Yes, exactly. So that's step one. And then the second thing is just and we won't show, I mean, this will be left as an exercise, but we'll need that tau delta of U of F tilde is F tilde of now delta op. So the theta that we have takes delta to delta twisted by tau, and then in order to actually get to delta op, that's exactly where this F tilde comes in. And so once we have that, we're good. And then the last thing is to, the final step will be that we note for U in U and X in V tensor W, if I act just on U tensor X by P, this was a calculation I did at the beginning. This is delta op of X of U of P X. And so the final point is that, I mean, we want to do R VW of U dot X. This is theta WV F tilde of P of U dot X. So this step 3 will give us theta WV F tilde of delta op of U PX. And then step 2 gives us theta WV of delta U F tilde PX. And then step 3 gives us that this is, I see there's tau there. This is delta of U.
And it's step 1.
Step 1, yes. Of theta WV, theta VW, I believe. No, theta WV. Of F tilde of P of X, and that's U acting on R VW of X. So basically there's kind of 2 trivial things, which is step 2 and step 3. Step 3, we stated at the very beginning. Step 2 is just something with how F tilde interacts with these 2 new co-multiplications, the opposite co-multiplication and the tau twisted co-multiplication. And then step 1 is, well, we need to argue this. And this will use a more kind of in-depth analysis of some of the calculations we did with the pairing between U minus and U plus. Should I start with that, or next? Should I start with that next time, or I'm just not sure. I don't want to go too late. Okay.
Okay, let's thank Elijah for the talk. And other questions?
Yeah, so maybe I want to make a comment. This formula that we got for the R matrix is not really a formula, because we're just saying that it's inverse to some pairing that is not so easy to compute.
Yes.
And so for SL2, we had a nice formula. So actually, for any Lie algebra, you can have a nice formula. And this formula can be obtained from a braid group action, which we'll discuss later, I suppose, right?
Mm-hmm.
Yes.
So if you have braid group action, you can actually write a formula for the R matrix, which is going to be just a product over positive roots of expressions similar to R matrix for SL2.
Yeah. Is this something we'll discuss, this formula?
I don't know. This is the boss who is.
I can't remember. I mean, I've seen this. It's like, maybe I'm not remembering.
That's right.
Well,
that's right.
We'll definitely write a formula for the for dual basis. I don't think that in present version of Calder's notes there is decomposition for matrix.
But it's easy to obtain from the quantum Y group, which is basically braid group.
Right. So we'll talk about quantum Y group action, and this will give us a formula for the dual basis.
Right. So what you wrote is right. So you should consider the W0 of quantum Y group and take delta W0 times W0 inverse tensor W0 inverse, something like this, and times T inverse cross T inverse. And then you can T is a product of T alphas, and then when you use that, you get a product formula for every reduced decomposition of the maximal element of the Y group.
Okay, so Pasha, you may want to communicate this to Calder.
Well, he probably knows how to do it. I just need to tell him that this should be done. I don't.
Yes, you can do this. I trust you.
Okay.
And
this formula is due to Lewandowski and Soiberman, by the way.
Okay. Other questions or comments?